Okay, students, so in the last video we saw how we aligned the interferometer so that we had Mach Zehnder interferometer so that we had the fringes visible, right? So it had to be perfectly aligned. So there were two arms, two paths, as we have discussed earlier. So light is going from here in one path. This is a beam splitter, so it gets to this path. The part of the light goes through here. There is a mirror here, which then reflects to this another beam splitter. So it goes like this straight. Let's say this light from this mirror then basically goes down here to this beam splitter, and again it gets reflected here and then it goes to the screen. Similarly, there is another possibility as well. For example, when it hits here, it can be transmitted, so it goes to this screen, right? And when light from this mirror goes there, it can be either transmitted or it can be reflected. So anyway, so whenever light is hitting those screen, there are two distinct paths, right? One path is from this arm, another path is from this arm, right? So we saw how we aligned in the last one and we got the fringes. So in this part, what you are seeing is that we have placed two additional components here. So this is polarizer 1, let's say, and this is polarizer 2. There are two different polarizers that has been put in the paths of these two light beams. Okay. So now light is coming originally from this laser. Okay. This is basically just a magnifier. So we had this earlier as well. So this magnifies the spot on the screen. Now these two polarizers are set at angles that are perpendicular to each other. Okay, what does that mean? Let's say this is at around 20 degrees, this is at around 110 degrees. So what is the angle between them? 90 degrees. So that means whatever light is coming from here, whatever is the direction of the axis, transmission axis or the pass axis of this polarizer, it will polarize that light along that direction. So the light after going through here is polarized along, let's say, 20 degrees, whatever is the direction, 20 degrees. So it goes from here. A part of the light is reflected at this beam splitter, it goes to that mirror. So that part then goes to the second polarizer, right? So this one then polarizes at 110 degrees. So the light going from this arm is now at 110 degrees. That means it is perpendicular to the light is coming from this arm, right? This first arm. So the two lights are now polarized perpendicularly. So what we saw earlier was a fringe pattern on the screen when we did not have the polarizer. So now let's say I have this polarizer. So now you see that there are no longer any fringes there. Sorry, you only see like a bright spot of light, no fringes. Okay, all right. So the fringes disappear the moment we introduce these two components, these two polarizers now. So in terms of quantum mechanics, you ultimately this is an analog experiment. So this is not a perfect quantum mechanical experiment. So it's a classical experiment that is meant to set up a situation that is analogous to a corresponding quantum mechanical situation. But this is not actually quantum mechanical phenomenon. So this is, you can explain this effect simply from classical point of view by saying that, okay, if we are interfering two waves, the two waves must be polarized in the same direction, or at least have similar directions, so that they can create fringes. So only if they are directed along the same direction, that means let's say they are 180 degree out of phase, they will be pointing exactly along opposite directions and they will cancel each other. So that is important for creating fringes, right? Bright and dark spots, bright and dark spots. So creating those dark spots, the two waves must be, for example, electromagnetic waves, let's say the electric field, the two electric fields must be pointing exactly opposite direction. So only then they can cancel out each other, right? So the waves must be polarized along the same direction, same line. That's the idea. If they are polarized along 90 degrees, they can never cancel each other, right? So there will always be a net electric field along the 45 degree to these two superimposing electric fields. So there is no question of any fringes there, right? There may be variation of intensities, but there is no dark, bright spots. So you can explain this classically. But quantum mechanically, what we are saying, let's say we think of these photons as particles. So that means as a wave particle duality. So they can be particle as well as waves. So we had these particles from this laser source, particles of light, photons from this laser source. Now the photons that were coming, they were behaving like wave. That's why you got the interference pattern there before we put the polarizers, right? So that means they could go through the even if I think of it in terms of one photon, let's say, so it is coming and it can go through both paths simultaneously because it's like a wave, so it gets split at the reflector, right? At this reflector. So it can go through both paths and then superimpose with itself and then create the wave pattern. Or there can be multiple photons. If I have a coherent source, there is one wave coming from here, maybe second continuous sort of waves or streams of photons are coming, so we are creating this pattern. But now by placing this polarizers, what I have done is basically now whenever because these polarizers are 90 degree to each other, whenever a photon is reaching there, just by looking at its polarization state, I can say which these two path it has come from. If it is at 20 degrees, it is coming from this first path, because this guy is polarized to 20 degrees, transmission axis around 20 degrees. If I observe that a photon is hitting the screen and it's polarized at 110 degrees, I can say it is actually coming from the second path, right? Because this guy is transmission axis is 110 degrees, this polarizes transmission axis. So just by looking at the polarization state of the photon reaching the screen, I can say which path it is coming from, right? So that means I have an additional information. So I have made an additional observation before the photon reaches that screen. So, and during making of that observation, as you know, a wave function will be collapsing to the eigenwave function for that particular eigenvalue, whatever you are getting, right? That's the postulates of quantum mechanics. So when you measure the polarization and when you determine the path, what thing has an exact path? A particle has an exact path, right? So the act of measuring this polarization or setting the polarization basically collapses the wave function so that it behaves like a particle, right? So that is why once it goes through these two arms, it is no longer interfering because it's now a particle. All right. So this is the quantum mechanical explanation. So this is like the quantum mechanical. If we had an exact quantum mechanical experiment, like with particles of photons, we could create one photon, two photons, like that. Individually, you can check. Then maybe we can have a exact quantum mechanical experiment, or you have particles of electrons and very well controlled system like two different slits. So then we can have a well defined. But this is an analog, so we are explaining it in analogous manner. So the act of placing the polarizers actually reduced these wave functions to particles. So now the wave particle duality is sort of gone. So because you have localized them, so they are now like particles. So particles will not interfere, right? So they do not give any interference fringes. Now you see, so basically this is also related to your quantum complementary concept, complementarity.